Hello, today we're going to be covering the triangle midsegment theorem. Before we can actually cover the theorem, we first have to understand the definition of a midsegment. The definition states that the midsegment of a triangle is a segment joining the midpoints of two sides of a triangle. If we look at the illustration on the left, we can see that F is the midpoint of the segment AC because it's cutting the segment in half. That E is the midpoint of CB because it's cutting the segment in half. So if we connect both of the midpoints with a line or with a line segment, we are going to create the midsegment. In the illustration here on the left, it's the orange line in the middle, right here, FE. Now for the actual theorem, the theorem states that the midsegment of a triangle, which joins the midpoints of the two sides of a triangle, is parallel to the third side of the triangle and half the length of that third side of the triangle. So part of the theorem is basically stating the midsegment definition, which we just covered a few seconds ago. That FE is the midsegment because F and E are both the midpoints of their corresponding segments, AC and CB. So for the actual part of the theorem, we can see that FE is going to be parallel to AB, which is the third side of the triangle, and that FE is also half the length of AB. We want to prove this theorem, but in order for us to prove this theorem, we have to first prove that FEC is going to be a similar triangle to triangle ABC using the SAS or the side angle side similarity of triangles so that we can obtain corresponding angles for parallel lines and establish a pair of proportional sides. So of course, we're going to have given information. The given information is that we have a triangle ABC and that F and E, again, are the midpoints. That's just basically the definition of a midsegment. And we want to prove that FE and AB are going to be parallel segments and that FE is going to be half the length of AB. In order for us to prove this, we're going to be using the two-column proof. The two-column proof basically has on one column, which is the left column, we have all of the statements, and on the right side column, we're going to have all of the reasons that justify our statements. So we first start off with the given information. Again, that triangle ABC, and then within that triangle, that F is the midpoint of AC, E is the midpoint of CB. So again, this is just the given information. Step 2 shows that FE is the midsegment because of the definition of a midsegment. Then that shows that AF is congruent to FC and that CE is congruent to EB because of the definition of a midpoint. Because F and E are midpoints, they're cutting the segments into two equal parts. Step 4, since the segments are congruent, then the segments measurements are also equal to each other. So this is by the definition of a congruent segment. Step 5, if we do a little bit of math here and there, using the segment addition postulate, we can see that if we add segment AF plus segment FC, we're going to get the long segment AC. And similarly, if we add CE plus EB, we're going to get the long segment CB. Using substitution, since AF is equal to FC, we can just do with a substitution so that we have FC plus FC is equal to AC. CE plus CE is equal to CB. Again, we're using the substitution based on step number 4. From here, we're going to do a combination of like terms. So we can use addition. FC plus FC becomes 2FC, and CE plus CE becomes 2CE. Solving for FC and solving for CE on their corresponding equations, we can use multiplication property of equality to get rid of that 2 in the front. So If we multiply times the fraction, we end up with FC is equal to half of AC, and that CE is equal to half of CB. This then shows that angle C is going to be congruent to angle C because of the reflexive property, and that triangles FCE, which is the top part, is going to be similar to the triangle ACB, using the side angle side for similar triangles. This then shows that the angle CFE is congruent to the angle CAB by the corresponding angles in similar triangles are congruent. And if we look at the picture on the left, we can see that the angles are going to be corresponding, since we just slide that upper angle all the way at the bottom and it makes a perfect match. From here, we have one part of our theorem proved, that FE is going to be parallel to AB because of the corresponding angle converse, which basically states that if two lines are cut by a transversal such that the corresponding angles are congruent, the lines are parallel. And then last but not least, our last and final step, that FE is equal to half the length of AB because of the corresponding sides of similar triangles are in proportion. And that concludes our proof for the theorem. Next, we are going to apply the theorem into two simple examples. Of course, the first example is the easier of the two, which says that we have MN to be midpoints, MN measure 12, and we want to find the length of DF. So using that mid-segment theorem, we can see that MN is a mid-segment by the definition. Applying the formula, MN equals to half of DF, we know that 12 is half of 24, which then means that DF, which is the third side of the triangle, is equal to 24 units. Our second example says that we have a triangle. Within that triangle, D and E are midpoints, that AB is equal to 26, and we want to find X. Now this one is slightly different because we are now working with an equation, but we still want to apply that same definition of a midsegment, that same theorem of the midsegment, and it's not as difficult if we follow the formula. So DE is the midsegment, which then means that DE equals to half of the measurement of BC, which if we do a replacement of the segment, 3x minus 5 is equal to half the length of 26. So 26 times 1/2 is 13. If we're solving for x, we have to move the 5 over to the opposite side by adding it. So 13 plus 5 is 18. We have 3x equals to 18. Solving for x by dividing by the number in front of the x gives us that x equals 6, since 18 divided by 3 is 6. And that concludes our lesson in triangle midsegment theorem. Thank you for your time.